There we go. Beautiful. Okay. Today we're going to talk about floating point. Okay. In particular, we're going to talk about fractional binary numbers, then the IEEE floating point standard, which is the sort of the standard that everyone is settled on. Some examples of properties, rounding, addition, multiplication, and then look at what's done in C. Okay, so we're used to thinking of fractional numbers, for decimal numbers in base 10, but the principles are the same. So if you look for base 2, if you look at this number here, what you see is 1011 to the left of the decimal point, right? And that's just 1 plus 2 plus 8, so that's 11. Okay, so that's easy to figure out. But what about to the right of the decimal point? Okay, well, right of the point. In decimal, as we know, the first digit is like the 10th digit, and the next one is the 100th digits, and then the 1000th digits, and so forth. Well, the principle is the same. It's just factors of 2, powers of 2. So it's the half, quarter, eighth, 16th. So what this represents here is, let's make this work. So that's a half. There's no quarters, and that's an eighth. And as we said, this is 15. So it's 15 plus a half plus an eighth. Okay. Okay, and in general, as I said, it looks like this. You've got everything to the this side of the decimal. This side of the point is powers of 2. Right, so the jth bit is 2 to the minus j, and everything to the left of the decimal point is powers of positive I, is the I position. Okay, and so there's a simple formula that should look very familiar if you're used to having a 10 there instead of a 2. Okay, if you're in decimal, but otherwise it's the exact same principle. All right, and so here's some more examples. If you look at that first one, you see that 5 3/4 can be represented as 101, which is 5, right? And then this again is a half, and that's a quarter. So it's shown here. It's 5 plus a half plus a quarter, which is 5 3/4. And similarly, we can represent 2 7/8 and 1 7/16, and it works out to be as shown. And you'll notice that the 3 examples I've given are you divide by 2 to get from one to the other. So this is divided by 2, this is divided by 2, and what happens with the bits is they just all get shifted, right? It's the same bit pattern, 1 0 1 1 1. It just gets shifted by one position, shifted right by one position. Okay. And in reverse is that if you want to multiply by 2, you just shift the bits the other way. And notice that if you have the number 0 and a bunch of 1s, okay, that's really close to 1. Okay, so because it's half plus a quarter plus an eighth plus 16th and so forth, and that almost makes it to 1. Okay, and so and the limit is the number. If you have increasing number of bits, you would get to 1, but in general, it's going to be 1 minus whatever whatever you've lost off the end. Okay, 1 minus epsilon. Okay, so there's some limitations that arise immediately, and the first limitation is that because that the base dictates what numbers you can represent concisely. Okay, so for instance, when the base is 2, I can easily represent a half, a quarter, and so forth, and 3/4 and things like that. But if I wanted to represent something like a third, then it ends up being not dividing evenly ever. So it ends up being this repeating sequence of 0 1 0 1 0 1. Okay, and similarly, fifth ends up being this repeating sequence of 0 0 1 1 0 0 1 1 0 0 1 1, and a tenth is that same sequence just shifted over because you've divided by 2. And so you notice that whereas in base 10, 1/10 was represented very simply, it's just 0.1. You know, and in a fixed number of bits, in base 2, 1/10 actually cannot be represented in a fixed number of bits, right? Just a repeating sequence. The second limitation is that there's only sort of one binary point in amongst the bits, and so where you decide to, you know, wherever you put that binary point, that sort of limits the range of numbers, right? So maybe you can get really large numbers or very small numbers, and we'll see how that plays out. Okay. So the IEEE floating point standard was you know, is established in 1985. Really, it's if you don't provide it, it's considered a very black mark against your processor. Okay, and so pretty much everybody provides it, even though it's really difficult to provide. Okay, it's a challenging standard to implement in hardware, and it's actually kind of interesting because if you think about how processors were designed, in many cases they were designed for what's easy to do in hardware. Okay, the instruction sets you get and so forth. A lot of things the hardware designers won, say, over software designers, right? That things get hard in software because the hardware designers just built what was easy in hardware. This is one case where the opposite happened. Okay, even though it was a pain to do in hardware, the numerical analysts said we have to have this, we have to have this, we have to have this, and so the hardware people, you know, companies bit the bullet and implemented this. Okay, and the reason is that the standard has very, you know, provides very nice standards for things like rounding, overflow, underflow. Things work out really well, you know, as well as can be, I guess, given you only have so many bits, and with nice mathematical properties that we'll see. That if you didn't have those, if you had something that was easier to implement but didn't have these nice properties, things would be really challenging for software writers in all sorts of ways. Okay, so you've probably seen representations like this. So you start off with a sign bit, okay? Then there are going to be some number of bits that are devoted to what's called the exponent of the EXP field, and then some number of bits that are devoted to the fraction. Okay, and the way that gets interpreted is that if you look at the number itself, the sign bit, if the sign bit's 0, then of course minus 1 to the 0 is 1, is 1, and so you get a positive. And if it's 1, then you get a negative. Okay, so that's how that works. Now, what's interesting is that this exponent here, okay, which represents what you want to raise the 2 to the whatever power, is not exactly what goes in these bits here, and we'll see why in a few slides. So instead it's just some encoding of the exponent, and then there's a way of translating from these bits to what the intended exponent is, and then you can manipulate them accordingly. Similarly, you have this significand M, okay, that gets represented with some number of bits in the frac, okay, but it's not going to be exactly the same, okay, and you'll see in a minute how they differ, okay. But you can represent things like the course number 15-213 in base 10 as in this expression as minus 1 to the 0 with a significand of the bit pattern shown there and the exponent of 13. Okay. One important point I should have mentioned is that the significand is always a fractional value that can be as low, is normally, and you'll see why that's a pun in a little bit, is normally a fractional value in the range between 1 inclusive and exclusive of 2. Okay. All right, so you may have heard of single precision and double precision floating point. Single precision is 32 bits. The way that's commonly divided is you allow 8 bits for the exponent and 23 bits for the fraction. If you have double precision, you allow 11 bits for the exponent and 52 bits for the fraction. Okay, and again, this is sort of by convention, right? I mean, there's no fundamental reason why you decide to put this many bits for the exponent and this many bits for the fraction. Okay, except that it seemed like a good compromise over the range of numbers people wanted to use, and because the exponent controls how big and how small of numbers you can have, right? And the fraction controls how precise can your numbers be. Okay, if you have a lot of bits of the fraction, then you can be more precise. All right. And then we're going to talk about that there's really 3 kinds of floating point numbers. There's the typical kind, which are the normalized ones, the ones in the middle, and that's whenever this exponent is not all zeros and it's not all ones. And then there's the 2 separated cases. One is where the exponent is all zeros, and that's called denormalized, and the other is where the exponent is all ones, and those are special ones that we'll talk about in a minute. But mostly you want to focus initially on these normalized ones, as they're the most common. Okay, so we have this exponent. Okay, so we have some number of bits for the exponent, and we want to be able to express both very large numbers and very small numbers. So we want to be able to have exponents that are both positive and negative. Okay. Now, we could have said, oh, well, we'll just use, our sort of sign number convention. We'll have the first bit be the sign bit, and the rest be the magnitude. But instead, they do something slightly different, where they have this notion of a bias. And the bias is when you look at the bits that are actually there, you want to subtract off this bias. So the bits that are there are going to be interpreted as an unsigned number. Okay, that are going to range from because we're not in these 2 cases, they're going to range from 1 to sort of the largest number you can hold in that many bits, minus the fact that we can't, we're not allowing the 111. So it goes from 1 to 254. As opposed to 0 to 255, because we're again, the normalized range truncates off those 2 endpoints. And so if those are the bits we care about, then we take those bits, that numbers, and we subtract off this bias, 127. And so what that allows us is to actually have exponents in the range between minus 126 and positive 127. Okay? And with double precision, that bias is computed differently, right? It's because you had 11 bits, it's basically 2 to the 10th minus 1, and so which is 1023. Okay, but it's the exact same principle. All right, so that's the sense in which what you see in those bits is actually not the actual exponent, it's the encoding. Okay, because you want to subtract off that bias. All right, now let's look at the difference between the significand, this m, and the bits you actually show up in the fraction part. So the first thing that happens is that there's an implied 1. Okay, so our mantis would be 1 point blah 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 blah, but because it's always 1 point blah blah blah, we don't need to store the 1. So it saves us a bit. Okay, so it's really all the other bits up to that point, and so it's minimized when this fraction is all zeros, right? And because of the implicit 1, that corresponds to 1.0. And it's maximized when this fraction is all ones, okay? And again, if you remember, that was the 0.11111 case is the case that's almost up to the next number. In this case, almost up to 2, but just minus a little epsilon. Okay, so that's what I meant when I said that the range of these things, at least in the normalized case, always falls between 1 and slightly less than 2 once interpreted. Okay, so let's look at an example. And here's our little cheat sheet here. Okay, this is what the value is going to be. It's going to be minus 1 to the sign, and you have the significant times 2 to the e. But the e is going to be computed by taking the bits that are there, this exp, and subtracting off our bias. So if we have this number here, okay, then if we put it into the form where you have a 1 followed by a dot, then the power you need for that is 13. So it's 2 to the 13th. Okay. And so what you end up with is all the rest of the bits become part of the fraction. Okay, and it turns out we have more bits than we need. Okay, so we pad out to 0. And the exponent, again, the goal is 13, but we want that to be the goal after we subtract off the values, so we have to add the bias to get the proper number of bits to put in there. And so that's 140, which is going to be represented as shown. And so the end result looks like this. Okay, and you can see how you can take a number like that and reverse it, right? So you say, okay, the sign that means it's a positive number, that exponent, which is, if you read the bits, that's 140, I subtract it from my bias, I get 13. And the fractional part, I interpret as putting a 1 dot in front of it, and I get exactly the value that I desired. Okay, any questions on that? All right, so that was the normalized case. Okay. So that can cover a large range of values, but you're sort of limited to how close to 0 you can get. Okay. If you recall, like for the single precision, we could get down to, bring it back up real quickly. Right, we could get all the way down to, exponent of minus 126. So I get a 2 to the minus 126. Okay, which you might think is really tiny, and you'd be happy, but it turns out that you often want to even get closer to 0. Okay, and so to allow for that, to sort of pack in more bits, pack in more representable values close to 0, we have this this special set in the exponent where we look at the values in a different way. Okay, and those are called normalized values. And so a couple of things are different here. One is that the exponent, instead of being, the e instead of being the bits minus this bias, like the 127, we're going to interpret that as 1 minus the bias. Okay? And then the significant is, instead of being encoded with a leading 1, is going to be encoded with a leading 0. Okay? So why might that make sense? Any ideas? Why the combination of those two things and the range of the normalized values makes sense for why you would start the normalized ones there? Any ideas? Yeah.
So that way you can get significantly smaller numbers than you could have before. This also allows you to, if you have all the bits in your fraction to be 0, you can actually just represent 0.
You can also represent 0. That's good. Yeah, I was talking more about the transition between these two regions, right? So in the one case, I was able to get to 2 to the minus 126. It was right. And then, the smallest number I could represent was 1.0 times 2 to the minus 126, right? Well, what's the largest number I can represent here, right? It's basically, 1 minus 127, so it's 126 again, okay? So you think, oh, well, that's kind of redundant. But now notice, because the mantisses start to 0, I actually start at things that are strictly smaller, right? The largest number I can represent is this one, right? So it's a perfectly smooth transition. I've gone from 1 times 2 to the minus 122nd to something just slightly less than that. Okay, so that's, for instance, why this is a 1 and not something else, right? Okay, so good. Special cases, as was mentioned, you have the all 0 case. It turns out that you can, because this doesn't account for the sign bit, we can have a positive 0 and a negative 0, once we look at the sign bit. In all the other cases, we get numbers that are equispaced and closer to 0 than anything we could represent with normalized values. Okay, so that was the denormalized case, and we'll look at some pictures of that in a second. But before we get to that, I want to talk about, yes?
So you're saying that the largest denormalized value and the smallest normalized value is the same value?
No, they're just epsilon apart, right? Yeah. Okay, so, good. All right. Okay, so now when the exponents are on the other extreme, where they're all 1, we interpret that differently as well. Okay? If the fractional part is all zeros, then that's going to represent infinity if the sign bit is 0, and negative infinity if the sign bit is 1. Okay, so this is represents 2 overflow cases, right? And there's some examples shown here, right? If you do 1 divided by 0, you get positive infinity. But you can distinguish that from, say, 1 divided by negative 0, which would be negative infinity, or negative 1 divided by 0. In every other case, where the fraction, except for the case where the fraction is 0, is not a number. Okay, a special thing called NaN, not a number. And that represents the cases where, it says here, no numerical value can be determined. So if you try to take the square root of -1, you're getting an imaginary number. If you try to do improper arithmetic with infinity, it's not a number, and so forth. Okay, so that's the two special values. Okay, so let's look at this in here. So suppose in C you had this hexadecimal number. Okay, and there's our hexadecimal cheat sheet. You should actually be getting really good at this by now if you've been doing the assignments. And this is our translation cheat sheet. Okay, so in this case, this is the normalized case, so you get the exponent minus the bias, as opposed to say 1 minus bias in the denormalized case. And let's consider the case of the single precision where the bias is 127. Okay. So this is the division between sign and exponent and fraction. Okay, and these are the things we want to be able to compute. And then when we've computed those, then we're going to be able to figure out the value by just plugging in our formula. Okay. Now, if we take that sequence, that hexadecimal sequence, and map it to binary, then C is this. 0A looks like that, and so forth. Okay, so that's just the bits spelled out. And then if you interpret those as the first bit being the sign bit, the next 8 bits, which are the red ones, being the EXP part, and the rest being the fraction part, it looks like that. And remember that our significant M starts with 1. Okay. So how do we get E? Well, we take that exponent, which if you look at that bit sequence, it's 128 plus 1, so you get 129. We subtract off our bias 127, and we end up with 2. Because that first sign is 1, we want a negative number. And if we look at the fractional part appended to 1 dot, then you get 0 halves and 1/4. It's 1 plus a quarter, so you get 125. And so this number, this floating point number, when the actual value of it is -5, because it's the sign bit times 125 times 2 to the 2, which is 4, and 1 1/4 times 4 is 5. All right, is that clear? Okay. So here's a little bit of a visualization. You can see that, as I've sort of touched on this, you've got all the normalized numbers that are bounded on the one side by the negative infinity, right, and the positive ones that are bounded by positive infinity. you've got the denormalized ones that are the closest ones to 0, and then you, special cases of that, you actually have the minus 0 and the plus 0. Okay, and clearly this isn't drawn to scale, okay, because the, you know, the denormalized numbers are tightly packed around 0. Okay, so just to look at some examples, we're going to actually view very short floating point numbers. Okay, so we call them tiny floating point numbers. So let's suppose you have one where that you're trying to represent an 8-bit representation of floating point numbers, and so we're going to allocate 4 bits for the EXP and 3 bits for the fraction. Okay, and based on the size of that EXP and the fact the bias is always to the that number of bits minus 1, then you end up with 7, and okay, and but everything else is going to be the same as what we talked about. There's going to be the notion of normalized, denormalized, and 0, not a number, and infinity. Okay, so what does it look like? So to keep the slide simple, we're only going to show the examples where the sign bit is 0. Okay, so just the positive ones, including the positive 0. So, I mean, you can stare at this later, but the main thing to remember or to note is that, okay, so we have 0 here, right? When everything's 0. All right. And then in the denormalized range, which are all these ones here in the white background, you have all the possible choices for the fraction. But for each of these, the exponent, because we're in the denormalized case, is going to be 1 minus our bias. And since our bias in this case was 7, they're all minus 6. You can see they're all minus 6. All right. Now, the values are going to be, you know, the represented here. So it's half, a quarter, an eighth, so that's 1/8. This one's, you know, half, a quarter, so that's 2/8, and so forth. This last one here is 1/1, that's 7/8. That gets multiplied by, you know, 2 to the minus 6, which is 1/64. And so here are the actual fractional numbers you would get in each of these cases. Okay, and you can see in blue we've actually plugged in the numbers, right? The 1/4 and the 2 to the minus 6, and that's what you get. Okay, and you know, the top one is closest to 0. The next one is the largest denormalized number. Now, as soon as the exponent flips to being non-zero, but before it gets to all ones, then we have the whole normalized range, and you can see that the so now we see a bit pattern like 0, 0, 0, but we have to remember that there's implicitly a 1 in front of that. Okay, so that's why this is 8/8. Okay, because it's basically 1.000. Okay, and now when we add one more, we get it to 9/8 and so forth. Okay, and but otherwise you're just, you know, plugging in a formula that looks like that, and you're showing what the numbers are. Eventually you get, you know, closest to 1 below, then you get 1, and then closest to 1 above, and then eventually you get to this, the largest normalized value you can represent, and then after that you get, you know, where the exponent is 1, 1, 1, and so it's the either not a number or infinity if the fraction is all zeros. Okay. So again, that's another way of thinking about how, or looking, using example to figure out how these numbers play out. So what, if you think about, well, what kind of numbers can I represent? What do they look like? Okay. And here's another way of looking at them. So here we've just to make it simple, we've even done a much smaller example, a 6-bit format, where you have 3 bits for the exponent and 2 bits for the fraction. And what we've done is we've plotted the denormalized ones, which are that middle slice there shown in black, with 8 values. The normalized ones, you can see how they sort of also concentrate closer to 0, and then the positive and negative 50. Okay, and if you zoom in just on that middle part, you can see that you know, there's your 8 values that include the positive and negative 0. Three values on each side of that, and then so forth to the other ones. So you can see from the figure that indeed the denormalized one are equispaced in there with whereas the normalized ones are sort of expanding out to the side in bigger and bigger jumps. Okay, any questions on that? So some properties of this, so if you recall, if every bit is 0, that's interpreted as 0, okay? And so that's nice because that means it's the same bit sequence as, say, a 0 and integers, right? And 2's complement, or unsigned, right? So that's good. The positive 0 is the same. The other thing that's interesting is that if you want to compare two floating point numbers, you can almost get away with just looking at their bits as unsigned numbers and comparing them. Okay? And you can sort of look at that if you go back to this thing here, right? So this was, the numbers were listed from smallest to largest. And if you just look at the actual bit patterns, you know, ignoring everything else, right? You can see that they do increase, okay? So, and you know, you can sit down and argue for yourself why that's true in general, not just for this example, but just as an intuition, you can see that if I just interpret those numbers not as 1, 4, and 3, meaning different things, but just as a single unsigned integer, they do increase as the numbers increase. Okay. But the almost part includes things like, well, we've got you know, a negative 0 as well as a positive 0, and we've got all these nands, right? But otherwise, it's okay. The normalized ones are indeed can be properly compared to the normalized ones. The normalized ones properly compared to infinity, and so forth. All right, good. All right, Canvas time. Participants. All right, people pretty much done?
A little bit more time.
All right, it looks like people have done pretty well. The first question was, a bit of a review. We're going to try to throw in like one review question just to keep you on your toes. Basically, if you're shifting by 8, that means you're moving the CA completely to the left of the F and the E, and so it ends up being cafe. That's the correct answer. So question 2 goes back to the example I gave earlier in the actually very beginning class, where I talked about how representing 1/10 can be done in a finite number of bits in base 10, but requires it's a repeating sequence. It's an infinite number of bits to get exactly right in, say, base 2. And so the answer for that is false, and most have got it right. And normalized, it means a lot of different things, but one of the things it does imply is that there's an implicit 1.0, a 1 dot in front of the fractional part, whereas with the denormalized ones, it's an implicit 0. All right, good. Any questions on the quiz? Okay, so now let's move on and talk about rounding, addition, and multiplication. Yes, question. I mean, you can certainly compare the bits, right? And they would be the same. Yeah, I guess for infinity, you could say they're equal, but like 2 neons are not equal, for instance. But for instance, as I had in the early example, if you take infinity and subtract infinity, that's not a number, right? So you don't get 0. So in that sense, they're not equal. It's a little bit complicated. Okay, so we want to be able to do arithmetic on floating point numbers, and we're going to talk about addition and multiplication. But because we only have so many bits in our representation, we're going to often need to do some amount of rounding. Okay, so we're going to take an answer that's the result of an addition or multiplication, say, and round it to fit within our representation. Okay. So you can think about different kinds of rounding modes, and we use this example here, where we want to round these 5 different prices, $1.40, $1.60, $1.50, and so forth, to the nearest round at the dollar, the dollar rounding. So in the first line, we show that if you round towards 0, then $1.40, $1.60, $1.50 all get rounded down to $1, right? $2.50 gets rounded down to $2. But maybe what's a little interesting is that negative $1.50, since we're rounding towards 0, will get rounded to negative $1. Okay. Then there's rounding down, which says no matter what, you always round towards negative infinity, right? So $1.40 rounds to $1, $2.50 rounds to $2, and in this case, a negative $1.50 rounds down to negative $2. The flip side of that is always rounding up. So in that case, say negative 150 would round up to negative $1, and 250 would round up to $3. But, you know, often, sort of an intuitive thing to do is to round to the closest. Okay? So if I do that to the nearest, then for the first three cases, it's obvious what to do. Sorry, first two cases. So for $1.40, the nearest dollar to that is $1. I end up rounding it down. For $1.60, the nearest dollar to that is $2. So I end up rounding up. But now I've got this $1.50, and that's like halfway in between. You know, what should I do? All right? So the policy of nearest even says that, you know, if you're halfway in between, okay, then you want to round to the nearest even. All right? It doesn't say always round an even number. It says only in the case you've got this tie you've got to break. Then you want to round to the nearest even. Okay? So $1.50, it's halfway in between. 50 cents is halfway in between. So the choices were either round up to $2 or down to $1. Since $2 is even, you round up to $2. $2.50, you round down to $2 to get to an even number. And negative $1.50, you round down to negative $2, again, to get an even number. All right? And that's the default rounding scheme that exists. Okay? That's why it's important to understand. Okay, so, and it's really actually kind of challenging to get the system to do anything else, right? You have to, do the manipulation yourself, in some sense. What the hardware supports is this round even. Okay, so that was the nearest dollar, but let's suppose you want to round to the nearest hundredth in this example here. So the nearest hundredth, of course, is you want to round all but the 2 bits off, right? So how are you gonna do this? If the obvious thing to do, again, is to look at these the digits that are to the right of where you're truncating, and if that's and then round to whichever direction is closest. So in this case, you're going to round down because that's less than halfway. In the next case, you're going to round up because that's greater than halfway. And now you have this tied case that we talked about last time. And so if you round even, then in this case, the choices were rounding to 7.89 or 7.90. And even in this case means the last bit is 0. Okay? And so you'd round to 90, okay? And, but in this case, the choice is between 0.89 and 0.88. And 0.89, the last bit of that is a 1. And 0.88, the last bit of that is 0. So in that sense, 0.88 is even, okay? Sort of this way of thinking about even. And so you'd round that to that. Okay? Is that clear? All right, so with binary numbers, it's actually in some sense simpler, right? Because there's only ones or zeros to consider. So if you want to round, so what does halfway look like? Halfway, is 1 followed by a bunch of zeros. So if we look at these numbers here and we say, okay, the digits in red are the part I'm considering when I'm deciding whether it's less than halfway, greater than halfway, and so forth. And so since 0, 1, 1 is less than halfway, which is 1, 0, 0, you round that one down. Conversely, the next one you round up because you're above 1, 0, 0. And now the last 2 cases are 2 cases where you're exactly at 1, 0, 0. Okay, and so now you want to round it to the even. Okay, so in this first case, right, the choices were to either round up to 11.00 or round down to 10.11. And clearly the former one is the one that's even. It's the one with the 0 in the last bit. And so that's what's shown, right? Conversely, this latter example, the choices were between rounding to 10.11 or 10.10, and the latter one is the even one, and so you round down to that. That clear? Good. So how is this done inside the processor itself, right? Well, it's given that rule, it's actually pretty simple. So if here is, if you're trying to round to the nearest eighth in this case, the three binary digits, we'll call the last digit is called the guard bit, which is represented as G. The first digit removed, first bit removed, is called the round bit, and then all the other bits are the sticky bits. And if you recall, the only pattern we really care about is distinguishing between a 1 and a bunch of zeros, and a 1 and something where there's not a bunch of zeros, right? And a 0 and something, right? And so if you look at all we care about in all these extra bits, all these X bits, is there a 1 in there or not? Okay? So that's just doing an OR. So the machine will do an OR over all these other bits. And so it will take any given fraction and represent those as okay, what was the guard, what was the round, what was the sticky? And so it's down to 3 bits. And so then it can build a little state machine to figure out what to do with the 3 bits. And if you look at our rules, you'd see that you don't want to increment in these 3 cases, and you do in these cases, and you get these rounded numbers. Okay? So the actual way it plays out is exactly the way I described in the previous slide. It's just, if you're wondering, like, well, how is this done in the hardware in a nice, convenient way, this is how it's done. All right? Okay. So now we know about rounding. Now we can start to do operations where we're going to need some rounding. Okay? And we're going to consider multiplication and addition. So multiplication, so in this case, we're trying to multiply this number versus this number. Okay, so each of those numbers has, when we look at the bit representation and we translate that back to an actual value, we know it has a sign and a significant and a exponent. Okay, and and we know the exact result, if we were to do full precision multiplication, would be that you take the product of the 2 significants, you take the sum of the exponents, right? 2 to the e1 times 2 to the e2 is 2 to the parentheses e1 plus e2. And then for the sign, you want to take the the symmetric difference, right? You want to if you have if both the signs are the same, then you know you're going to end up with a positive number. If one's 0 and one's and the other's a 1, then it should be a negative number. Okay. So that's what would happen if you computed it exactly. Okay, but that form is not going to be in the right form necessarily. So we have to fix it up. All right. So for instance, if now we have a mantissa, a significant that's no longer 1 point something, right? It's bigger than greater than or equal to 2. Then we fix that up by simply shifting the whole thing to the right and incrementing the exponent, right? Right, because we, by shifting to the right, we're dividing by 2, and to maintain the same number, by incrementing e, we're multiplying by 2, so it's the same number. Now, if the exponent is out of range, then we just have to do an overflow, positive or negative infinity, and then the fractional part, which is the translation of this after the shifting, I guess. We want to truncate it to the right number of bits, and we want to do that in a way that respects our rounding rules. Okay? All right, good. So let's look at a quick example. If our original number is, it looks like this, okay, and we want to multiply by this, then again, we got 2 to the 2 and 2 to the 3, so we add those 2 exponents and we get 2 to the 5, right there. Okay, and we take the product of 1.010 and 1.110, and you could do that quickly if you wanted, but they, and you confirm that this is the answer, right? 1.0, 10.0011. Okay, so that's the exact result. Now we have to fix it up. So we fix it up by, since this is bigger than, since m is now bigger than 2, we shift this thing to the right, so that's why this is just shifted to the right, and we add 1 to that exponent. Okay? So all we're left to do now is to round. We want to be able to round this to say, three bits here. Okay, but we have 5 bits, and so we look at the bits we're truncating, and we see we're actually much closer to rounding up than to rounding down, and so that's why we round up. And you get a 1. Any questions on that? Good. All right, what about addition? So addition, as you learned in elementary school, you've got to get the decimal points, or in this case the binary points, lined up, right? In order to add, you got to put them in the right column. So that's the first process, right? Is just try to line up those binary points, right? So you shift this over by E1 minus E2, and then you can actually do all the addition of the bits, and you get some sort of exact result. Okay, and okay, and then we're going to take the exponent to be the larger of the two, right? Because that's what we're kind of doing when we line it up. We match it to the larger of the two. And then we have to do this fixing, right? So again, if m is greater than or equal to 2, we want to shift to the right and increment this exponent and so forth. I should have said, actually, in multiplication, actually, maybe we're okay. I was a little worried that if we might have to repeat the shifting more than once if it's like, say, bigger than 4, but I guess you can't get it to be that big because both these numbers are less than 2. Okay, never mind. We're good. All right, you just have to do that at most once. And similarly with addition, you just have to do it at most once. But we have this other situation with addition that maybe we've ended up with a really small number. And so, it's after we do the subtraction, it's 0.0000 blah, 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 before we get into ones. And now it's not in the canonical form of a 1 followed by a bunch of zeros. And so we fix that by shifting the other way. We shift this number here. If this is the first 1, we shift this number over here, so the 1 is that side of the decimal point. And then to keep the exact same value, we have to decrement the exponent by how many positions we shifted. Okay. We're going to overflow if the exponent is out of range, and we're again have to do rounding with the fractional part to make it fit. Round the significant m to make it fit. So an example here. Okay, so we have our two numbers, and the first thing we do is we line up the decimal points. We do that by making them representing them both in as times 2 to 3. So for the larger one, the bit pattern is the same, right? It's just, but for this one, we shift it over by 1, right? Because 1.01 times 2 to the 2 is the same as 0.101 times 2 to the 3. Right? So now we've got them lined up, and now we can do the addition, right? 0 plus 0 is 0, 0 you get a 1, 1 you get a carry, and you end up with 1 0 0 1 1 0. Okay, and notice that's bigger than 2. So we do the trick of shifting to the left and incrementing from 2 to 3 to 2 to 4. Okay, so now everything's good except for we have to do our rounding. So let's suppose that we have just 3 bits to represent the fraction. So that's where we're looking to round. And so here it's 1 0. So that's the tie, that's the halfway in between. And so we want to round to the nearest even, which is this, right? And the choices were to either round to 1.001 or 1.010, and the latter is the even. Okay. Any questions? Yeah, is that a question? Okay, so so with that in mind, so we just did addition. Okay, so the question then is, you know, how well does this work in terms of preserving the properties that we'd like to have in addition? Okay, and the answer is pretty well, with some exceptions. Okay, so is our way of doing floating, you know, is the IEEE standard for floating point addition way of doing addition closed under addition? Okay, and the answer is yes, although you may get like an infinity or not a number. Is it commutative? Is, you know, x plus y equals y plus x? Again, you can check for yourself if that's true. Is 0 the additive identity? If we add any floating point number and 0, do we get back the floating point number? The answer is yes, so that one's good. Okay. Does every element have an additive inverse? So for every element, is there a sort of a minus of that element such that we add them together, you get 0? Again, that's almost true. The only issues are with infinity, negative, infinity plus infinity, and the non numbers. So as long as you're staying out of that range, we're good there as well. Monotonicity says that if A is less than or equal to B, is greater than or equal to B, and we add something to it, the same quantity to both sides, is it still greater than equal to, the first side is still greater than equal to the second side. And again, that turns out to be true, except for the special cases of infinities and nans. Okay? So you can see that basically 5 of these 6 properties that we'd like to see in any representation of numbers holds just fine. And so that's one of the very nice things about, you know, about the standard and so forth. So the catch, and this is a big catch, if you're ever doing any sort of numerical computation, and this was touched on in the very first lecture, the overview lecture, is that you lose associativity. Okay, that basically because of the overflow and the fact you have to do some rounding means that you know, you can take the same 3 numbers and just associate them differently, and you get very different answers. Right? So in the second case, you have 2 small numbers. They're represented exactly. You can subtract them. You actually get 0, and then you add it, and you get the right number. But over here, this large number, this very large number, dwarfs the 3.14, and so it just gets truncated away. It's as if you never added it, and so then when you subtract off this same very large number, you're actually going to end up with 0. Okay, so this is a serious problem in numerical computation. Is how do you design these things to so that rounding doesn't kill you? Right? How do you set up the problems? Your you know, huge mathematical simulations and so forth of you know, weather patterns and things like that, so that rounding doesn't kill you. Right? Right? Or if you're the you know, a manned spacecraft, right? Then rounding could literally kill you if you did it wrong. Right? Okay. What about multiplication? Here the news is pretty good as well. All right. It's closed under multiplication. You know, it's commutative. 1 times anything is still that value. And so the multiplicative monotonicity says that if A is greater than or equal to B, and you have a non-negative C, then if you multiply that C by both sides, then the sense of the inequality doesn't change. And that is also true except for infinities and for the nans. Okay, so this is pretty good as long as you stay out of the range of infinities and nans. Okay, multiplication, however, has the same problem with associativity. Okay, you get weird rounding effects. And similarly, you know, we all know that multiplication distributes over addition in real numbers in general, and in certainly things like integers. But because of overflow and inexactness of rounding, you can come up with examples where it doesn't work. That A times B plus C is not equal to A times B plus A times C. Okay, good. All right. Any questions on that? Yes.
Do we take overflow into consideration when talking about the properties?
You take what?
Do we take into consideration overflow into consideration when talking about properties, mathematical properties? Because even integers don't always hold true when in terms of monotonic.
Yes. So you're saying even under like integer addition, integer multiplication, we have these exceptions.
Yeah.
Because of overflows. Correct. Yeah.
So we don't take overflow into consideration when we, let's say, this property is true.
Well, I think you have to understand you have to. Well, I mean, the overflow in this case will generate infinity, so that's perfectly fine. If you recall, like say for unsigned integers, the way to think about the result was always modulo, 2 to the whatever number of bits you had, right? And so under that, field, that finite field, right, wrapped around modular arithmetic, then all these properties held, right? Because it sort of took an overflow out of the picture by saying, oh, well, what we're really arguing is that when viewed as modular arithmetic, it all holds, right? All these properties hold. Here, we're sort of taking it out of the picture by saying, well, we have this infinity symbol, and so that's going to catch everything. Yeah, that's really a nice subtle point. Glad you brought that up. Okay, good. All right, so what about in C? So C has, you can declare something to float, which is a single precision, or a double, which is double precision. And now let's look at casting. So if you take a double or a float and you cast it into an integer, then what happens? Well, it will just truncate the fractional part. Just drop all the fractional part, you get the integer. And so that's equivalent to rounding towards 0. Right? You just got rid of all the bits 0. And it's not defined when you're out of range, not a number. Generally, it will set it to t-min in those cases. Like for instance, if a double could have many more bits than the int could hold, right? And so, it's not defined if you're out of range. Int to double, as long as the int has word size such that you can actually represent all the bits in the double. So in this particular case, it's a 53-bit word size or less. So like if you had 32-bit integers, then you don't lose any precision converting double. Okay, there's enough bits there in the representation to cover all the integers. And for float, where you often don't have enough bits, it will just do the rounding move. Okay, so given that in mind, let's do a few puzzles. Okay, so is this true? If I take an integer x and I cast it to a float and then back to an integer, do I get back the original x?
Not necessarily, because if the int takes up more than 23 bits.
Right, it'll get rounded. Good, very good. Okay, what about for a double? What does it say about doubles? Works out just fine, right? Because there's enough bits. As long as the int is, less than 53 bits. What about this one? I start off with something that's a float, I cast it to double back to a float. Does that work? Yeah. Okay. What about the other way around? Take a double. No, you're going to lose a lot of bits there, right? Should be good, right? This may have bit you in a few C programs in your past. Right, 2 divided by 3 without the decimal point is interpreted as integer division, so it would be 0. Once you put the decimal point in there, it's going to be interpreted as floating point arithmetic. So you'd get 0.66. If I have a double that's negative, I'm going to multiply by 2. Is it still negative? So it's multiplying by 2. Is it still negative? Okay, that's fine, right? I mean, even if I end up overflowing, it doesn't change the sign of it. Right? It never changes the sign of it. So I get negative infinity. Okay. If I have a double that's bigger than a float, is the negative float bigger than the negative double? Okay, no issues there. If I square a number, it's non-negative. Or sorry, if I square a number, it's always non-negative. That's what that's asking. Somebody tell me why?
Could be not a number. Could be because of zero.
Well, okay, so we're assuming here, sorry, I should have pointed that out. Assume in these examples that D is not.
Yes.
Okay, why? It doesn't change the sign. I mean, sorry, the sign is always going to be, the sign bit is computed independently, right, of any overflow or underflow. So it's, if they're both, if D is positive, it'll be a sign bit of 0, symmetric difference with a sign bit of 0, and if it's a 1, they're both 1s, so you get a sign bit of 0. So that's going to be true. All right, what if I take a double and add it to a float, and then I subtract back off that double? I get back the float. What goes wrong? It's a rounding, right? Okay, good. So in summary, we have this IEEE floating point standard that has, is a real pain to implement in hardware. Exactly right. But the vendors were forced to do it, and they've done it. And so we have this standard that has very nice mathematical properties, well understood mathematical properties. You represent numbers in the form a sign bit times the 2 to the e. You can reason about the operations independent of any implementation because this is the standard. We showed you how to do that, compute with perfect precision and then round. It's pretty close to real arithmetic, but there's some gotchas, especially in terms of sensitivity. Okay? That's it for today.